Gluons are elementary particles that act as the exchange particles for the strong force between quarks, analogous to the exchange of photons in the electromagnetic force between two charged particles. In technical terms, gluons are vector-gauge bosons that mediate strong interactions of quarks in quantum chromodynamics. Gluons themselves carry the color charge of the strong interaction. This is unlike the photon, which mediates the electromagnetic interaction but lacks an electric charge. Gluons therefore participate in the strong interaction in addition to mediating it, making QCD significantly harder to analyze than QED. Properties. The gluon is a vector boson. Like the photon, it has a spin of 1. While massive spin 1 particles have 3 polarization states, massless gauge bosons like the gluon have only 2 polarization states because gauge invariance requires the polarization to be transverse. In quantum field theory, unbroken gauge invariance requires that gauge bosons have 0 mass. The gluon has negative intrinsic parity. Numerology of gluons. Unlike the single photon of QED or the 3 W and Z bosons of the weak interaction, there are 8 independent types of gluon in QCD. This may be difficult to understand intuitively. Quarks carry 3 types of color charge. Antiquarks carry 3 types of anticolor. Gluons may be thought of as carrying both color and anticolor, but to correctly understand how they are combined, it is necessary to consider the mathematics of color charge in more detail. Color charge and superposition. In quantum mechanics, the states of particles may be added according to the principle of superposition. That is, they may be in a combined state with a probability, if some particular quantity is measured, of giving several different outcomes. A relevant illustration in the case at hand would be a gluon with a color state described by. This is red as red ante blue plus blue untitled. If one was somehow able to make a direct measurement of the color of a gluon in this state, there would be a 50% chance of it having red and blue color charge and a 50% chance of blue untitled color charge. Color Singlet states, it is often said that the stable strongly interacting particles observed in nature are colorless, but more precisely they are in a color singlet state, which is mathematically analogous to a spin singlet state. Such states allow interaction with other color singlets, but not with other color states. Because long-range gluon interactions do not exist, this illustrates that gluons in the singlet state do not exist either. The color singlet state is. In words, if one could measure the color of the state, there would be equal probabilities of it being red untitled, blue anti-blue, or green anti-green. 8 gluon colors. There are 8 remaining independent color states, which correspond to the 8 types, or 8 colors of gluons. Because states can be mixed together as discussed above, there are many ways of presenting these states, which are known as the color octet. One commonly used list is, these are equivalent to the Gell-Mann matrices. The translation between the two is that red untitled is the upper left matrix entry, red anti-blue is the upper middle entry, blue anti-green is the middle right entry, and so on. The critical feature of these particular 8 states is that they are linearly independent, and also independent of the singlet state. There is no way to add any combination of states to produce any other. There are many other possible choices, but all are mathematically equivalent, at least equally complex, and give the same physical results. Group theory details. Technically, QCD is a gauge theory with SU, gauge symmetry. Quarks are introduced as spinor fields in NF flavors, each in the fundamental representation of the color gauge group, SU. The gluons are vector fields in the adjoint representation of color SU. For a general gauge group, the number of force carriers is always equal to the dimension of the adjoint representation. For the simple case of SU, N, the dimension of this representation is N2 or 1. In terms of group theory, the assertion that there are no color singlet gluons is simply the statement that quantum chromodynamics has an SU, rather than a U, symmetry. There is no known a priori reason for one group to be preferred over the other, but as discussed above, the experimental evidence supports SU. Confinement. Since gluons themselves carry color charge, They participate in strong interactions. These gluon-gluon interactions constrain color fields to string-like objects called flux tubes, which exert constant force when stretched. Due to this force, quarks are confined within composite particles called hadrons. This effectively limits the range of the strong interaction to 10 or 15 meters, roughly the size of an atomic nucleus. Beyond a certain distance, the energy of the flux tube binding two quarks increases linearly. At a large enough distance, it becomes energetically more favorable to pull a quark-anti-quark pair out of the vacuum rather than increase the length of the flux tube. Gluons also share this property of being confined within hadrons. One consequence is that gluons are not directly involved in the nuclear forces between hadrons. The force mediators for these are other hadrons called mesons. Although in the normal phase of QCD single gluons may not travel freely, it is predicted that there exist hadrons that are formed entirely of gluons called glue balls. There are also conjectures about other exotic hadrons in which real gluons would be primary constituents. Beyond the normal phase of QCD, quark-gluon plasma forms. In such a plasma there are no hadrons. Quarks and gluons become free particles. Experimental observations: quarks and gluons manifest themselves by fragmenting into more quarks and gluons, which in turn hadronize into normal particles, correlated in jets. As shown in 1978 summer conferences, the Pluto experiments at the Electron-Positron Collider Doris reported the first evidence that the hadronic decays of the very narrow resonance Y, 9.46 could be interpreted as three jet event topologies produced by three gluons. Later published analyses by the same experiment confirmed this interpretation and also the spin-1 nature of the gluon. In summer 1979 at higher energies at the Electron-Positron Collider again three jet topologies were observed, now interpreted as QQ-Gluon-Bremsstrahlung, now clearly visible, by TASSO, Mark J. and Pluto experiments. The spin-1 of the gluon was confirmed in 1980 by TASSO and Pluto experiments. In 1991 a subsequent experiment at the LEP storage ring at CERN again confirmed this result. The gluons play an important role in the elementary strong interactions between quarks and gluons, described by QCD and studied particularly at the Electron-Proton Collider HERA at DESY. The number and momentum distribution of the gluons in the proton have been measured by two experiments, H1 and ZEUS, in the years 1996 till today. The gluon contribution to the proton spin has been studied by the Hermes experiment at HERA. The gluon density in the photon has also been measured. Color confinement is verified by the failure of free quark searches. Quarks are normally produced in pairs to compensate the quantum color and flavor numbers. However, at Fermilab single production of top quarks has been shown. No glue ball has been demonstrated. Deconfinement was claimed in 2000 at CERN SPS in heavy ion collisions, and it implies a new state of matter, quark-gluon plasma, less interacting than in the nucleus, almost as in a liquid. It was found at the relativistic heavy ion collider at Brookhaven in the years 2004-2010 by four contemporaneous experiments. A quark-gluon plasma state has been confirmed at the CERN Large Hadron Collider by the three experiments ALICE, ATLAS and CMS in 2010. See also, quark, hadron, meson, gauge boson, quark model, quantum chromodynamics, quark-gluon plasma, color confinement, glue ball, gluon field strength tensor, exotic hadrons, standard model, three jet events, deep inelastic scattering. References. Further reading, A. Ali and G. Kramer. Jets and QCD, a historical review of the discovery of the quark and gluon jets and its impact on QCD. European Physical Journal H36, 245 326. AR Ziv, 1012.2288. Bibcode, 2011 EPJH. 36245 doi, 10.1140 E 2011-10047-1A.